Hi, I'm Matthew Hardy, and I'm going to be presenting population-level amplification of perceptual bias. So this is joint work I've done with Bill Thompson and Tom Griffiths, who are at Princeton, and Peakscraft, who's at the Oxford Internet Institute. In this paper, we conducted a large-scale, multi-generational experiment testing whether social transmission increases people's cognitive biases. One possibility is that it does, and it isn't hard to think of contemporary examples where social media and other forms of transmission appear to be making people more biased and also more polarized. And what we're experiencing here is only a snapshot. Interaction on social media is increasing and transmission is accelerating. Social transmission leading to long-run bias amplification is actually a prediction made by anthropologists in the 1980s. However, this theory was focused on semantic biases and hasn't been extended to cognitive biases, and it also hasn't been experimentally tested. On the other hand, it could be that multi-generational social processes actually help people overcome and reduce their cognitive biases. Collective intelligence research shows that social interactions can lead to smarter individuals. Furthermore, cumulative processes, like science and technology development, indicate that these benefits could also accrue in generational networks. However, studying multi-generational societies experimentally has traditionally been out of reach. To examine these two possibilities, we performed a large-scale, multi-generational behavioral experiment that measured the impact of social transmission on people's cognitive biases. In our experiments, we chose to focus on motivated perception, a cognitive bias where people overestimate the probability of high-utility events. To give some intuition on how this bias operates, I'd like to quickly go over one of the iconic studies on motivated perception. So in 1951, Princeton and Dartmouth played an infamously rough game of American football. Players on both sides were seriously injured, and both sides blamed the other for the mayhem. A few years later, Hastorf and Cantrell, two psychologists, coincidentally one at Princeton and one at Dartmouth, ran a study where they showed undergraduates at both schools scenes like this one, and asked them to evaluate what happened and who was at fault. Unsurprisingly, when watching the same scenes, Dartmouth students tended to think Princeton players had fouled, and Princeton students thought Dartmouth players had fouled. This tendency for people to interpret ambiguous events in ways that are good for them is known by a number of names, such as motivated perception, motivated seeing, and wishful seeing. For simplicity in this talk, we'll stick with motivated perception. We focused on this bias as it seems to be a significant factor in the public divide in opinions on climate change and on other social and political issues. That means that if we can get a better understanding of how motivated perception operates in experimental networks, we may also better understand the processes behind real-world public polarization. So we want to induce a similar bias in a more controlled experimental paradigm. To do so, we used a numerosity estimation task where participants briefly viewed images and decided whether they contained more green or more blue dots. This setup gave us tight control over both the ground truth and the difficulty of different stimuli, and as we'll see, allowed us to turn the motivated perception bias on and off for different participants. Before going into how we induced biases on this task, I'm going to go over how we set up the experiment for control participants with no biases. We gave these participants a cover story in which they worked for a company looking for green emeralds and blue sapphires, and their job was to judge whether different areas contained more green emerald dots or more blue sapphire dots. So here's an example of what a participant might see. Pay attention because the stimulus only displays quickly. Alright, so you can try and think of what the answer was, but this person chose emerald and chose correctly. All participants that chose correctly received a small accuracy bonus. So again, the version we just saw before was a control version with no motivated perception bias. To induce this bias on this task, we changed the cover story slightly so that participants looked for green emeralds in blue water and had to choose whether areas contained more green emerald dots or more blue water dots. The motivated perception bias was then induced by giving participants an unconditional bonus for every green emerald dot on each stimulus. In line with related work on motivated perception, we hypothesized that this would bias participants towards overestimating the number of green dots. That is, the more green dots there were, the better it would be for the participant, and so they tend to think there were more green dots than there actually were. However, because this bonus was unconditional, it wouldn't influence a classically rational decision maker. So here's an example of what participants in this green bias condition might see. So here, this person got the answer wrong and thought there were more blue water dots, and so they didn't receive an accuracy bonus. However, they still got the green dot bonus, as they get this bonus regardless of whether their choice was right or wrong. To prevent our results from being confounded by color biases, we randomized which color participants were biased towards. To bias participants towards blue, we told them that they were looking for blue sapphires in green grass. And these participants received an unconditional bonus for every blue sapphire dot. To ensure that participants understood this bonus structure, we gave them 2 practice trials with full feedback and had them take a comprehension quiz before starting test trials. We also organized the stimuli symmetrically so that participants would choose their bias color on exactly half of the trials on average if they were unbiased. All right, so in this study, of course, we're interested in how social transmission influences motivated perception. In order to test the theory of bias amplification from cultural evolution, we focused on generation-structured social networks. And as we touched on at the beginning, we also think that this setup captures the temporal dependencies and open-ended structure characteristic of many social processes. We built this generation structure into our experiment by recruiting participants in batches or generations. So we started the experiment by recruiting the first generation of participants, and their choices were all asocial or made in isolation. After each participant in the first generation completed the experiment, their choices were aggregated and summarized, and then the next generation was recruited. Every participant in the second generation viewed the same summarized choices of first generation participants before viewing each stimulus. This process was then repeated for several generations, allowing us to study long-run social transmission in a single experiment. So here is what the transmission looked like for participants. Before viewing a stimulus, they first saw the choices made by participants in the previous generation. So here the social information helped the participant make the right choice, but also pushed them towards choosing their bias color. We call treatments where social information was transmitted social treatments, and treatments without transmission asocial treatments. However, asocial treatments were recruited using the same batch structure as social participants, but there was no transmission between generations. All right, and lastly, in our methods, I'm going to go over the experimental design. So we used a 2x2 experimental design, crossing social transmission with the induced bias. This gave us 4 treatments and allowed us to isolate and compare the effects of both individual bias and social transmission on people's choices. For each treatment, we ran independent networks of participants. For the asocial no bias treatment, we recruited 8 generations with 8 participants in each generation. Each participant completed 8 test problems, and we replicated each of these networks 10 times. Again, even though these participants were recruited in batches and assigned to networks, they didn't observe any social information. The same setup was used for the asocial induced bias treatment, and the same for the social treatments. The only difference for the social treatments is that they only had 7 social generations because the first generation was asocial. So this left us a sample size of 2,400 participants and 19,200 judgments. This experiment was designed to test the predictions of both older theories from cultural evolution, as well as a computational model we built to extend these theories and make predictions about cognitive biases. This model is set up by embedding resource-rational Bayesian individuals into a larger distributed process, and then comparing this process with a distributed inference algorithm. In our model, the first asocial generation of participants makes their choices by combining their prior expectations with the observed stimulus, a pretty standard approach to modeling individual cognition and behavior. The key to our model is to assume that the choices of one generation will serve as the prior distribution for the next generation's hypotheses about the same stimulus. And this setup may be looking familiar to people who have worked with sequential Monte Carlo methods. Specifically, it shares formal structure with a set of distributed inference algorithms known as particle filters. What's cool about this model is that it allows us to characterize the population-level computation being performed and make precise predictions about long-term social dynamics. When biased individuals are included in this model, we get two predictions. First, that bias will accumulate and increase across generations, and second, that information will accumulate and increase across generations. That is, we predicted that participants in social treatments would be both more biased and more accurate than participants in asocial treatments. All right, so we ran this experiment on Amazon Mechanical Turk over several days, and we're going to start with looking at our findings on accuracy. So this bar shows the proportion of people in the asocial no bias treatment that successfully identified the correct majority color. And the red bar shows the same for participants in the asocial with bias treatment. These estimates are averaged over all networks, generations, and participants, and the error bars are computed from a mixed effects logistic regression with replication as a random effect, which we did to try and control for the non-independence of judgments within specific networks. Again, these stimuli were set up so that a participant choosing randomly would choose correctly 50% of the time. So we found that asocial participants performed significantly better than chance, and that their performance wasn't affected by the motivated perception bias. But also note the scale here. Participants in both treatments still got many answers wrong. This is by design. We wanted a task that was difficult. However, when we look at people in social networks, they perform significantly better than asocial participants. As predicted by our particle filter model, and extending related work on collective intelligence, information accumulated in social populations and improved people's choices. And this boost in accuracy wasn't significantly affected by the bias. And so we found that while bias didn't impact performance, social transmission significantly improved it. In the same way that we looked at accuracy, we can look at how the motivated perception bias was expressed in asocial and social populations. So here the y-axis shows the proportion of people's choices that reflected their bias. Exactly half of all biased participants received bonuses for blue dots and half for green dots. So the arrow here shows the proportion of biased choices we would expect if people's choices were unaffected by the dot bonuses. In line with the literature on motivated perception and reasoning, we found that people's choices were, in fact, biased towards their motivated color. But this bias was relatively weak in individuals. So instead of choosing their bias color on 50% of trials, asocial biased participants chose it on about 56% of trials. However, when participants were part of a social network, they were significantly more likely to choose the color that they were biased towards. This more than doubled the magnitude of the bias, so that participants in social networks chose their bias color on over 62% of trials. That is, social transmission amplified a bias that was relatively weakly expressed in individuals. All right, to wrap up, I'd just like to review our findings and then discuss how they relate to the larger questions that we're interested in. In this project, we designed a simple perceptual task that gave us tight experimental control. We used this task to induce a bias towards a certain color for participants in bias treatments, and dropped this into batched social networks. Participants in all treatments performed significantly better than chance, but participants in social networks performed significantly better than asocial participants. However, social participants were also significantly more biased than social participants. So, coming back to our original question, does social transmission amplify cognitive biases? We found evidence that yes, it does. We think this is important not only because it allowed us to test long-standing theories, but also because it shows how cognitive science and experimental psychology gives us new ways of thinking about complex social issues. All right, I'd like to thank my collaborators again, and we're happy to answer any questions you have in the video chat or via email. Thank you for your time.